Welcome to the AbsInt Videocast for our April release in 2021. My name is Christian Humbert and I'm going to present the latest features in our binary level analyzers, StackAnalyzer, aiT WCAT Analyzer, TimeWeaver, TimingProfiler, and ValueAnalyzer add-on. Here is an overview on the new features that I'm going to present to you in this release video. First, as usual, let's get started with the overview on the changes in the graphical user interface, followed by some improvements in the value analysis and the aiT path analysis. I'd like to conclude in this release video today by a lot of new AIS2 specifications that I'm going to present. The graphical user interface can now show the number of iterative decoding rounds for each analysis, and I'd like to show you that using some example. I've loaded a special version of our scenarios example, and here I have some analysis IDs, and I'd like to use the very first one because that one, the 1 millisecond task, has exactly two decoding rounds, as you can see here. The very first one, here's grayed out since the value analysis encountered some new information that could be helpful to resolve more computed calls automatically. And so we have a second decoding round, and this was obviously the last one. So now you can visualize the number of decoding rounds here in the overview by just modifying the columns here. Right mouse click to any of the columns in the overview. You can say edit columns, and you can also add the decoding round property here. And for instance, you can move it here and say OK. And now you see, well, for this analysis here, it took 2 decoding rounds, while when we execute the next one, as you can see, we just have one. We have just one decoding round. Next bullet on our list is the extension of the AIS annotation editor in the graphical user interface. It has now been extended in a way that annotations that are associated with info, warning, or even error messages are marked correspondingly, and it allows you also to directly jump back to that message. And that's a very helpful feature, I guess. Let me show you that. Let's stay here in the 1 millisecond task for a while, and let's disable the dependency to our initialization analysis, which was responsible for resolving the computed call automatically, so that I get a computed call warning now when I restart the analysis. You see the computed call in the 1 millisecond task has not been resolved now automatically, and I have prepared the AIS file correspondingly. So there is an annotation to resolve this computed call correctly by extracting all computed call targets from a constant table called message handler table. And we are talking about the handler component actually. So if I use this annotation now to resolve the computed call, we will see the following. The computed call is resolved, but there is some hint here, which you just find by heart, I would say, that there was a null pointer extracted while extracting the handler components here. And this is actually associated with our annotation, as you can see here in the link. But now you will also find here a small icon together with the orange arrow indicating the program location in the graph. You also have a reference back to the original message. This is new in this release, and so you can jump to that message. Well, I was there already, so let me just quickly go somewhere else and click again to the show message, and you end up exactly at this ignoring null pointer target message. Well, and if you want to, as you know, if you want to skip the null pointer while decoding, anyway, then you can use the skipped null attribute, and then the message is gone. You see, there's no link back to a message, and there's also this ignoring null pointer message here gone away. The next improvement affects the graph visualization. Here we have improved the history view and made it much more convenient to use. Let me give you an example. For that, I'm going to load the 10 millisecond task analysis and open the graph visualization. So let it make a bit bigger here, so we have a full view on our call graph. And now maybe I'm interested in investigating our func3 here, and then I would like to set a marker of the current view in the graph. You can do that by clicking here on this history symbol. Here we have introduced new navigation buttons to add history markers, to remove them again, and to clear the entire list of history points. So let me set a marker here and then switch to some other place in the graph. Here I'm in proc 8, maybe I'm interested in investigating the loop here. And this is an interesting point to save another marker here. All right, now I would like to come back to func3, and this is quite easy now by just double clicking on my marker here, and I'm jumping back to the location where I was before. To come back to proc 8, to our loop, just double click again and we are here. Next is our loop bound statistics. Here we have extended the statistics by showing both the analyzed and user annotated loop bounds in case of an AIT analysis. So let's stay for a moment in the 10 millisecond task. Here I have the ARS file, and as you can see, the user has provided here 3 different loop bound annotations for func2 L1, proc0 L1 and proc0 L2. Now that we have done the analysis, we can switch to the statistics, the loop bound statistics, and you actually now see these values here for the annotated min and max bounds. So remember, for func2 L1 we had 0 to 15, for proc0 L1 0 to 20, and for the L2 0 to 10. The interesting thing is that we also visualize or show here the min and max bounds which the analysis automatically determined, and in this case actually the analysis was able to prove that the bound has to be left already after 2 iterations in this loop, and here this is those 2 loops are left immediately after 1 iteration. So the annotated max has been restricted by the automatically determined max, but you can see still the original annotated values here. For the first 4 loops, you see that there was no annotation for the loop bound, so it stays 0 to inf in this case. But luckily the analysis was able to bound them automatically. For the last point on my GUI features list here, let me explain. There was a need for introducing a new ARS file called pre-included ARS file. You will find it under setup files. Here, in addition to the global ARS file, we will also find now a pre-included ARS file. All specifications, all definitions in this pre-included ARS file will be processed before the global ARS file is processed, and even before hardware settings in the graphical user interface, especially, or for example here in the stack pointer or stack area field, will be evaluated. That way you can define your own labels or defines in this pre-included file. In my case here I defined a core local stack label, which I'm referring here in the graphical user interface settings, in the hardware settings. You can see here in the ARS file that my label was defined here I'd like to go into more detail of this annotation here later in our section about the new AS2 specifications. Now let's talk about the value analyzer. You are maybe familiar with the fact that it can implement a static memory protection. And we have improved the output of this static value analysis in this new release, and I'd like to give you some demonstration on it. For that, let me switch to a separate value analysis of the 1 millisecond task. I can do it right here. And let us have a view to the source code of the 1 millisecond task. As you can see, inside of that task, in line 131, the CAN message buffer is actually accessed. But this CAN message buffer has been initialized before in some initialization function here, being either a reference to the message buffer 0 or the message buffer 1, depending on some define here, if we are talking about CAN device equals 0 or 1. So in our configuration here, the CAN device is set to 1. That means that our CAN message buffer is assigned to be the message buffer 1. In other words, that also means that the message buffer 0 shall never be accessed during the entire task execution. And we can formulate now such a static assertion in AIS. Let's do it like this. Let's go to the AIS file. You start with the keyword routine, then we would like to restrict our static assertion to our task 1 millisecond CAN routine. And our area is the, let's copy it from the source file, the message buffer 1. Sorry, message buffer 0. So if we copy it to the buffer here, paste it here, then we open a scope, and inside of that scope we say we would like to assert that this is readable false and also writable false. So now this is our static assertion, and if we rerun the analysis now, let's see what happens. Well, the assertion goes through. There's no violation of the reassertion, and this is expected since we never use the buffer 0, right? So what do you think happens now if we change it to the message buffer 1? Well, then hopefully we will get some assertion violation, because the message buffer 1 is accessed, as we have seen. It is written, and yes, you will get here a report message, an error, that some definite assertion failures have been detected, right? And you should follow the report file to see more information. Let's do that. Let's go to our local report file and go to the section assertions here. And we will find our output. And in this release version, we now also protocol that the protected area, which was our buffer, has been read or written, and we also report which actual address has been accessed out of this protected area. So this is a bit more detailed now and gives you better information. Now let's come to the AIT path analysis. You may get some infeasible problems if there are some conflicts between your default loop bound and some analyzed results. In previous release versions, it was not that obvious that a wrong default loop bound would cause these infeasible problems. Now in 21.04, we are introducing a new contradiction warning in the AIT path analysis. Let's give some example. For that, let's switch to our 10 millisecond task analysis here and perform the analysis. You see there are some 3 loops here for which a default loop bound of 4 was applied. Remember, the default loop bound is configured here under setup, timing analysis, default loop bound. It is set here to 4. In this example, my analysis precision was quite low, the standard precision, and especially I unrolled the loops here just twice. We distinguished the very first iteration from all other iterations and distinguished 2 different contexts for it. But what happens now if I'm increasing the precision to a default unroll value, which is actually higher than my default loop bound? Let's see what happens. In this case, now the analysis is able to prove that there is some contradiction. It says that the string copy XL1 default loop bound of 4 contradicts the analyzed result of that loop, which cannot be left until round 5 at the earliest. It cannot say if 5 is the right loop bound, but it especially knows that the annotated default loop bound of 4 is not enough. And these kind of contradiction warnings, which we also get here for the memcopy in this case, will now be issued and gives you some indication on that your default loop bound is chosen not correctly. Of course, in a perfect way, you would annotate these loops individually, by using right mouse click, copy AIS annotation, and put here some loop specific bound, which has to be higher than 5. I'd like to continue now with an overview about the new AIS2 specifications coming with this release, and there are quite a lot of new features to discuss here. The first new specifications are the accessing of global attributes that are now defined by each analysis run, and they can be accessed via this special attribute keyword and used within if scopes only by comparing the attribute's contents against some value. And what kind of attributes we define now? Well, for instance, the architecture we are currently running on, and in my case it was a project for the architecture ARM, for instance. You can request or check the analysis ID, the analysis type, if it's a stack analysis or a WCT analysis, for instance, an analysis configuration the current analysis item is running on, and the analysis group in which the current analysis is contained in. So let me give you an example here. For instance, you could provide such an if scope where you check the current architecture. So only if we are talking about the tricore analysis here, then we check another attribute, which is the analysis configuration. Only in case if the current analysis has been defined for core 1 configuration, then we would like to turn all functions here of the name functhandle core 0 or 2 into infeasible, because if we are running the task on core 1, the handle core 0 or 2 functions can never be accessed. Let me give you another example here inside of the analyzer. So if we go to our example here, is the first millisecond task, and as you can see, we have provided here several configurations. This first millisecond task is running on core 1. We also have a configuration core 0, and now remember we had this pre-included AIS file, right? In this pre-included AIS file, we checked the attribute here, the actual analysis configuration. If we are running on core 0, then we would like to define a new label called core local stack symbol from the beginning of some stack core 0 object to the end of the same object. If we are running on core 1, which is the other core, then we define the very same label, but this time we are beginning at stack core 1 and go until the end of the stack core 1 object. So that means now if I come back to our analysis here, the first millisecond task, it's running on core 1. Let me just run this analysis. Then we see that our stack pointer here begins at 67B0. Remember, we had set it here under setup hardware to the end of our core local stack object, which we have defined in the pre-include file. And now if we are changing it to core 0, for instance, then the annotated user stack will change correspondingly. So instead of just defining different stack pointer values here for each configuration, we can keep the very same expression here in these fields, but set it configuration dependent in our pre-include ARS file. The next new feature is something many of our customers have requested so far. It's accessing hash-defined macro information via the DWARF debug information and using it inside of ARS annotations. It becomes available through two new functors. The first one is the macro functor, where you address the macro name and optionally give the program point at which the macro information becomes available. Note that it becomes available only one line after its definition in the original C file. The return of this macro function is a string value, and with the evaluator functor eval C, you can evaluate that C string to get the integer value, for instance, out of the macro. Let me give you an example in the analyzer. For that, I'd like to switch to my first millisecond task analysis. And remember, we had this unbounded loop here left, this warning. So we can have a look to the source code. It's a for loop, which depends on the message length. And the message length actually is set here in an initializer to some macro value, the can message max length. That was defined here, as you can see in the C code, to value of 32. Okay, now we have already collected all information we need to bound that loop, but I would like to show you some give you some tip. You can go to information. There is the macros view, and you can extract the DWARF macro information here. And we have learned it was defined in the scenarios file, so you can unfold that. And here you will see all macros that have been defined in this source file. Of course, there are many which are coming in via the compiler itself. But at the very end, I think you will find our own macros. See, here they are. Among others, we have the can message max length here, which has the value of 32, right? And it also shows in which file, at which line, this macro has been defined. And now you can do just a right mouse click, say copy ICE annotation, and it saves us the macro expression here in the required format. So this is a nice way to get the right syntax. So we can go back to our ARS file. Here it is, our local ARS file. We can paste it here. Of course, for complete loop bound annotation, we also need the ARS template. So let's do right mouse click here, copy ARS annotation, and put it here. And instead of instantiating here the value 32, we would like to do it more robust and access the macro, right? So let's do it like this. So let me make it a bit more compact. Ending it. So this unfortunately will not work yet because we are just accessing the string value of the macro. So if I run the analysis, it still does not take any effect, yeah? Because it does not evaluate the string value into a constant. So we need to put around the eval_c operator as well, right? And then if we do that, the right loop bound is applied. So we can do a right mouse click and say show loop statistics, and we see now it has been annotated by this 32. Now, let's make another example. So we are going back to our scenario C file, and here's another macro defined. It's called error mode. It's either defined to be NVM disabled value or NVM enabled, depending on the underlying architecture. So just a quick check, in our binary it was set to, as you can see here, I've selected it already here under macros, error mode has been defined to be NVM disabled. So we can use that macro information inside of our IS annotation, again by just copying here it in the paste buffer, going back to our AIS annotation file, and we can keep it here and surround it by an if scope. We can check if this macro value, if that one was NVM disabled, only then I would like to turn our OS error hook into infeasible. And well, this can also be copied here by the graph. So right mouse click, infeasible, where is it here? Going back, we put it inside our scope. Okay, so if we rerun the analysis, now it should become infeasible since we have seen our error mode was set to NVM disabled, right? And if we go back to the graph, you see it was turned into infeasible. And if you redo the analysis with a different binary where this error mode has been set to enabled, then the routine will be part of the analysis. So we can simulate that, of course, shortly. The other way around, if we check it to enabled, then the analysis should encounter still the OS error hook. So you can really formulate very generic annotation files with that. The next new feature in ICE is introducing comments in the call and control flow graph. So let's see how this works. If you go to our 10 millisecond task, open the graph, and for instance, we are going to Func1. You see this is the standard visualization of our basic blocks, the instruction level in our basic blocks. Now you can do at arbitrary program locations, you can set a textual comment besides of that instruction. So you can go to here, copy ICE annotation and say comment, which is a new entry in this context menu. And then you can go to your AIS file and set it here and say, well, this is my first comment in Func1. Okay, and maybe you want to add another one at this place. Say right mouse click. Oops, I don't see it here. Sorry. Again. And go back and say, well, this is my second comment. That's it. And if you rerun the analysis, then you can imagine that, well, first of all, these are of course linked back to the graph, but you will also see it here inside of the graph. It's indicated by some nice message indicator here on the function level, and where you see the comments already. But if you unfold it here, going down to instruction level again, you really can see these comments, and this helps a lot in, for instance, understanding what the binary instructions implement, so you can really provide some helpful comments here. Last but not least, I'd like to introduce a new functor. It's the IntervalFunctor. It evaluates a sub-expression to the least representative interval that still contains all the values from the sub-expression. So for instance, if you had, if the sub-expression was a set of constant values, if you put the IntervalFunctor around, that gives you the interval containing all, or the entire value range containing all values of that sub-expression. In this case, -1 to 9. Alright, this concludes my presentation of the latest features of the April release 21. As usual, this was just a small subset of all new changes and improvements. A complete list can be found on our website. Thank you very much for your interest. Take care and goodbye.